Metal G or Insect Jew, a red monster star on the verge, is a galactic wonder. Assuming that you put it where the sun is, it would reach out to the circle of Jupiter. It's huge, entirely temperamental, and it's going to detonate. Prepare for a vast fiasco of never-before-seen scale. Betelgeuse, the red Goliath star on the edge of our cosmic system, is conveying startling messages through space. Cosmologists have tracked down something profoundly disturbing about this huge object, utilizing the James Webb Space Telescope. Famous researcher Brian Cox has given an intense admonition. The question that continues to come up is, are we going to observe a cosmic explosion blast that will change the night sky for eternity? The riddle of Betelgeuse in the boundlessness of the universe is that stars are conceived, live, and die in astounding ways. As of late, one star has grabbed the eye and worry of both space experts and the general population. Betelgeuse, a red supergiant star in the constellation Orion. It is amazingly monstrous and old. Its special rosy variety and changing splendor have long been captivating. Yet late events have uplifted interest in this vast monster. As we find out more about Betelgeuse, we are very near a potentially great event in its history. But what could these changes in Betelgeuse mean? Are we seeing the start of a grand, real display on an incomprehensibly enormous scope? Betelgeuse's enormous size and life cycle are staggering. Betelgeuse is a heavenly giant, roughly 1,000 times bigger than our Sun. Its size is nearly beyond human ability to grasp. Imagine a star so massive that if it supplanted our Sun, its surface would reach out past Mars' orbit, wrapping Mercury, Venus, Earth, and Mars. This huge size not only delineates the actual greatness of Betelgeuse but also shows its stage in the heavenly life cycle. As a red supergiant, Betelgeuse is approaching an amazing finish, extending and cooling after depleting the hydrogen in its center and combining helium. The age and development of Betelgeuse are also notable. This star is estimated to be between 8 and 8.5 million years old. While relatively young in human terms, it is ancient in cosmic terms. Over millions of years, Betelgeuse has undergone emotional changes, evolving from a hot blue star to the red giant we notice today. It is now in its last stage as a red supergiant. Stars like Betelgeuse change throughout their lives due to the ongoing tensions of atomic fusion and gravity. Another trademark that makes this phase of Betelgeuse stand out is its remarkable ruddy color. Its red tone emerges from its cooler surface temperature compared to other stars like our Sun. Its brilliance changes, and historical records show the Sun's surface is around 5,500 K, while Betelgeuse's surface is around 3,500 Kelvin. This cooler temperature permits Betelgeuse to emit light at frequencies that make it appear red. However, this tone is more than just an appearance. It reveals information about the star's physical state and the processes happening inside its tremendous gaseous volume. The fact that Betelgeuse's color has changed over time adds to its mystery. Historical records from Roman and Chinese times indicate that Betelgeuse was yellow as recently as 1,000 years ago. By the 9th century, Arabic astronomers noted its red color. This change over the course of human history isn't just a historical reference. It signifies the star's evolution. An interesting part of Betelgeuse is its changing splendor. It is a semi-regular variable star, meaning its brightness fluctuates periodically. This musical dimming and brightening have thrilled researchers and astronomers for centuries. Commonly, Betelgeuse undergoes a multi-day cycle and a longer 5-year cycle. As early as 1836, Sir John Herschel documented these cycles, and native people's narratives may go back even further. However, what really makes Betelgeuse strange isn't just its brightness changes but their inconsistency. Unlike many stars that fluctuate in brightness predictably, Betelgeuse sometimes deviates from this pattern, suggesting complicated and less understood processes inside its huge structure. Recently, space experts and astronomers were stunned to notice a dramatic and unexpected change in Betelgeuse's appearance. This phenomenal darkening has raised various kinds of speculation. This is now known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the most brilliant stars in the night sky and a noticeable feature of the constellation Orion, began to diminish mysteriously. The star was dimming so quickly that it started losing its light at a pace of 0.01 magnitudes per day on average. By February 2020, it was at its dimmest. Oddly, Betelgeuse, which can typically be seen with the naked eye even in areas with significant light pollution, became much fainter, and even casual observers could notice the difference. The mystery of time and light delays complicates observations of Betelgeuse's activities. Since light takes such a long time to reach us, when we observe a star like Betelgeuse, we are not seeing it as it is now but as it was in the past. For Betelgeuse, the light we see today left the star nearly 725 years ago. This delay makes predicting and observing rapid changes in its behavior challenging. Andrea Dupree, the representative head of the Center for Astronomy at Harvard and Smithsonian, and her team closely monitored Betelgeuse's heavenly show as part of a 3-year study to track changes in Betelgeuse's outer atmosphere. They used the Hubble Space Telescope to observe the massive star. These observations provided new insights into how a variable star like Betelgeuse works. Variable stars constantly grow and contract, causing changes in their brightness. Scientists were able to examine the layers above Betelgeuse's surface, somewhat heated by the star's swirling convection cells. Thanks to Hubble's sensitivity to ultraviolet light, further investigation of Hubble spectra taken at various times in 2019 and 2020 revealed the development speeds in Betelgeuse's upper atmosphere, the discharge of material, and its results. The spectra were primarily composed of magnesium, showing that material was moving from Betelgeuse's surface into its environment at about 200,000 miles per hour. This hot, dense material eventually traveled thousands of miles away from Betelgeuse, forming the dust cloud that darkened the star during the 3 months of the eruption. Dupree and her team estimated that about twice as much material as expected was ejected from Betelgeuse's southern hemisphere. While all stars lose mass over time, Betelgeuse's mass loss was especially notable because it occurred at a much faster rate than the Sun's. Astronomers wondered whether this event could signal an impending supernova. Given the size of the mass ejection and the subsequent dimming, being nearly 725 light-years away from Earth, Betelgeuse adds to the intrigue as any such blast would be observable from Earth and offer an exciting opportunity to study a supernova up close. The question remains, what does this darkening mean for Betelgeuse's future? Is it an indication of an inevitable supernova? Or is it just a one-time event in the star's long and complex life? Several theories have been proposed to explain this rapid transformation. One popular theory suggests it was a precursor stage in the supernova process, gaining momentum due to the belief that Betelgeuse is nearing the end of its life. Another theory suggests that dust, possibly from the star itself, was obstructing our view. It is known that Betelgeuse and other red supergiants shed material, which could accumulate into a dust cloud thick enough to block the star's light. A third theory examined how changes in the star's photosphere, the apparent outer layer, could affect its apparent brightness. This mystery was addressed using a mix of observational methods and in-depth analysis. Spectroscopic investigations and findings showed that Betelgeuse's effective temperature had dropped, suggesting that the star might be dimming due to a large dark spot on its surface. The fact that Betelgeuse's temperature decreased by at least 170 Kelvin around the time of the darkening supported this idea. This indicated massive changes on the star's surface. Eventually, the Hubble Space Telescope, humanity's sentinel in space, helped us understand what was happening with this rare event. Hubble's observations showed that the darkening of Betelgeuse was likely due to a large amount of hot matter being ejected into space. This material formed a dust cloud that darkened part of the star's surface, reducing the amount of light reaching Earth. The dust cloud was thought to consist of extremely hot plasma that emitted from large convection cells on the star's surface. As this plasma traveled through Betelgeuse's hot atmosphere to cooler outer layers, it formed dust grains that created a cloud, blocking light from about a quarter of the star's surface. The impact of the ejected material was clear from Hubble's ultraviolet light spectroscopic examinations, which began in January 2019. These examinations were crucial in sorting out the events leading up to Betelgeuse's darkening. They identified dense, hot matter traveling through the star's atmosphere months before the dimming. Several ground-based telescopes also noticed the star's brightness decline in December 2019, with Hubble's observations confirming these findings and providing further insights into the ejected material. The discovery that Betelgeuse was losing material at a much faster rate than previously thought led to the realization that this rapid mass loss could affect our understanding of stellar evolution, especially in red supergiants. It's important to understand that Betelgeuse isn't the only star going through such dramatic changes. Other historical supernovae, such as SN 1054 and SN 1987A, have provided significant insights into how stars die and how new elements are formed. These past events have helped shape our knowledge of stellar deaths and their impact on the surrounding space. For example, SN 1987A, which occurred in a neighboring galaxy, offered a close-up view of a supernova explosion and its aftermath. Such supernovae contribute to the galactic cycle by scattering heavy elements and influencing star formation potential. The blast of Betelgeuse, if it ultimately becomes a supernova, would create a spectacular light show visible from Earth. The explosion would be brighter than the moon and could even be seen during the day. Such an event would provide an exciting opportunity to study the final stages of a massive star's life, as well as the development of cosmic structures and the spread of heavy elements across the universe. Despite the dramatic nature of a supernova, the distance between Betelgeuse and Earth provides an infinite safeguard, ensuring that such a blast is unlikely to directly harm our planet. In conclusion, the insights gained from observing Betelgeuse's potential transformation will continue to advance our understanding of stellar evolution and cosmic phenomena. The role of red supergiants in stellar evolution is vital to our interpretation of cosmic growth. These stars represent the final stages of a massive star's life cycle before it undergoes a supernova explosion. Their enormous size and relatively short lifespans make them excellent laboratories for studying the end phases of stellar development. Red supergiants play a crucial role in understanding how massive stars evolve, as well as the processes that lead to their explosive deaths. These stars have a huge impact on their surrounding environments. The energy they release in their final stages contributes to the formation of heavy elements, which are essential for the creation of planets and life. As we know as we look into the depths of space. Stars like Betelgeuse are our cosmic window into understanding the universe's most mysterious processes. Betelgeuse's future remains a topic of intense scientific interest, especially as we witness the changes happening on the surface of this giant star. Understanding the behavior of stars like Betelgeuse can help astronomers develop more precise models of stellar evolution and unravel the fate of not just individual stars but entire solar systems. A red supergiant like Betelgeuse represents one of the final stages in a star's life cycle. These massive stars burn through their fuel at an astounding rate. Unlike smaller stars such as our Sun, which can last billions of years, red supergiants only survive for a few million years. The sheer size and mass of these stars make their internal processes highly dynamic, and ultimately they succumb to an explosive death, a supernova. It is through these violent deaths that red supergiants enrich the universe with heavy elements, such as iron, gold, and uranium. These elements are critical for the formation of planets and, by extension, life as we know it. In Betelgeuse's case, its core is likely already composed mainly of iron. This iron core is important because once it reaches a critical mass, the fusion process within the star will collapse. As the core shrinks under gravity, it heats up, and the outer layers of the star are expelled violently. This rapid collapse is what initiates a supernova, an event that sends a shockwave of energy and debris into space. If Betelgeuse does indeed explode, it will not only light up the night sky but also provide invaluable data about the final moments of a massive star's existence. One of the fascinating aspects of Betelgeuse's dimming events is the way they might offer clues to the star's internal processes. Typically, stars like Betelgeuse exhibit gradual changes in brightness over time, which are linked to their ongoing life cycle. However, the rapid dimming observed in late 2019 and early 2020 raised alarms among astronomers. The rapid decrease in brightness could be the result of a large ejection of material from the star's outer layers, which formed a dust cloud that partially obscured the star's light. This sudden drop in brightness could indicate that the star is in the final throes of its life, with the outer layers shedding significant amounts of mass in preparation for the ultimate explosion. The possibility of a supernova occurring within the next few thousand years is still speculative, but it is a tantalizing prospect for scientists. Betelgeuse's supernova could have important ramifications not just for our understanding of stellar evolution but also for how we study such explosions from Earth. A nearby supernova like this would allow astronomers to observe the physical processes involved in a stellar death in real time. The explosion would release a tremendous amount of energy, including light and neutrinos, and by studying these emissions, scientists could gain new insights into the mechanics of supernovae and perhaps even the formation of black holes. Supernovae are not just interesting because of their dramatic nature. They are also responsible for the creation of heavy elements that form the building blocks of planets and life. When a massive star explodes, it scatters these heavy elements into the surrounding space, enriching the interstellar medium with the raw materials necessary for future generations of stars and planetary systems. These elements, formed in the hearts of dying stars, are the very elements that make up the Earth and other planets, and are the foundation of the chemical processes that support life. In this way, the death of stars like Betelgeuse plays a fundamental role in the cosmic cycle. The expansion of Betelgeuse's outer layers is another important feature of its life cycle. Over the past several decades, astronomers have observed that the star's outer atmosphere is growing in size. As Betelgeuse loses mass, it is shedding material into space, but it is also swelling to enormous proportions. This expansion is a characteristic feature of red supergiants, and it plays a significant role in how these stars interact with their environments. The outer layers of the star are primarily composed of hydrogen and helium, and as the star expands, the pressure and temperature in its core increase, accelerating the fusion process. The star's outer layers will continue to expand until they reach a critical point, at which time the core will collapse, triggering the supernova.